Okay, so yeah, we shall start and yeah. So we're going to start with the 9 axioms of Zermelo-Fraenkel, including the axiom of choice, and that would be, for the most part, what we will do with set theory and a brief section on equivalence relations and stuff like that. So that'll be what we'll do with sets, and then we'll go back to functions. So, okay, so Zermelo-Fraenkel theory is kind of the most well received kind of set theoretical framework that most mathematicians work. Well, there are still controversies about it, but at least that's the one that we're going to use. Okay, so we have 9 axioms, right? So the first axiom is about the axiom of extensionality. Right, so this is actually the axiom that like defines how you're going to deal with the members of each set. So like the epsilon relation, right? Um, the belongs to relation, and that is defined with this axiom, right? So this says that two sets are equal, that is, they're the same sets if they have the exactly same elements, right? So again, this is a brief side note, but if there is one intention that you should put through while like dealing with sets or sets essentially, is that the goal is to always try to go from using words to using logical symbols and operators and stuff like that. So here I've tried to write down for each axiom the way you would like mathematically write it, using logical operators and symbols. There are a few typos, but that'll be fixed. So the goal is, you should like develop the kind of thinking which results in like when you see this kind of like sentence, normal sentence, you can think of the mathematical format of it in symbols, and this will be very useful when you go to writing proofs, which is the most important thing in an algebra course. Um, the axiom of extensionality says that if your set A is equal to B, so this actually should be uppercase B, A is equal to B. Uh, so when you say this, this is actually saying that A is equal to B is a statement that is true, right? So this is what the parentheses mean. So it's a statement that is true. Then that statement being true is equivalent to saying that for all x in A, it's equivalent to all the elements x in B, right? Um, and so this is the symbol for and, such that for all the sets A in X, you can like equivalently write down B, all the sets B in X. So this lets you use the epsilon relation, the members relation with sets. Yeah, that was the first axiom, and yeah, it doesn't really have any kind of like anything else to say, but that's just pretty much it. And also, I forgot to say, but when I'm talking, this is not really a lecture student kind of format. You can actually speak whenever you like to. You can just either interrupt or you can say anything in the text chat. Um, but yeah, this is supposed to be interactive and a discussion kind of thing. Okay, so we have the second axiom. The second axiom is about regularity. So this makes it clear that every set that is non-empty must contain a member, right? So it must contain another set within itself, such that the parent set and this set, the other set B, are actually disjoint, right? So they don't have any elements in common between them. So the axiom can be written down in this manner. So there exists a B in A, such that for all the lowercase b, the elements in capital B, it is never equal to any of the elements lowercase a in the set A. Right? So that's the disjoint property, right? one of the interesting corollaries of this axiom is that if you have such a pair of set, you can say that the only set that is actually a member of both of those sets, is actually the null set, the empty set, right? So that's fine. Um, and indeed, you can't really state this without actually having this as an axiom. So this is the axiom, and then you have the corollary. And then from the corollary, you can actually have the theorem that there is actually only one empty set. And this is a theorem you can try. This would be a good exercise actually of like dealing the axioms. You can try to prove that actually there is only one empty set possible. The way is to assume assume with the intention of contradiction that there are two empty sets, and then you try to follow from the axiom of extensionality, and then you reach a contradiction that two sets cannot be the empty set. Okay, and there's the other interesting thing about these two axioms is that the Russell's paradox. This is actually mentioned in Alufi. Mentioned, I don't think in the sections, but it's in the exercises. It's not on the P set, certainly, but it's in one of the exercises that you have to understand what the Russell's paradox is. So if we go back a bit, I think we can find it. No, I thought it would be here, but it isn't. Okay, let me get back to my set theory notes. Mm, yeah, so this, wait, yep, this is the Russell's paradox. I just forgot which file it was. The Russell's paradox says that if you have a set A, if you have a set X which contains A, and A is not an element of A, then is X an element of X? So essentially, it's asking like, is um, the union of such A's is it going to be X? Um, and the answer is no. And there is actually a proof for this, which is interesting. What's more interesting than the proof itself is like how to think about it. And it's kind of paradoxical, but this is actually pretty straightforward from the axiom of extensionality and the other one about the disjoint sets. With using those two, you can prove it. Okay. So yeah, that was the axiom for regularity. Okay, so now we have the third axiom, which is for the schema of specification, but it's more generally known as the axiom of restricted comprehension. And this can kind of sound daunting, but it's kind of very straightforward. So you have a set A, and on this set A, P of X is a property, any property which characterizes the elements X of the set A. So if you have that, then there is a subset B of A which contains the elements of A that satisfy the property. So mathematically, what you can do is write that for all X, so here X is a set. For all the sets X, you have this property P of X, which is defined as picking out all these A's from the X such that P of A is true. So P of A being true means that this property holds for this element, right? So this element has the characteristic that the property is trying to look for. So if you have that, if you have such a property P of X defined on X, then there exists a set Y such that all the elements in Y, for all the elements in Y, this holds, right? So P of B is true for all the elements B. So what that means is that all the elements of Y satisfy the property, right? And thus you get Y as a subset of X, right? Okay, so that was the restricted comprehension axiom. Then we have the axiom for pairing, right? So this is important, especially the direct result is the Cartesian product, if you know about it. Except that's a very special case. You have an ordered pair, but this is just any arbitrary pair. So if you have two sets A and B, then there exists a set which contains A and B as its elements, right? So you can, if you have A and B as sets, then you can have another set in which A and B are elements, right? So you have the set X and set Y. Then you can say that there exists some set M such that for all U in M, uh, it is equivalent to saying that U is equal to X and Y. So X and U, right? So the thing is, every element U of M is either going to be X or is going to be Y. Okay. So what that leads to is having a pair X and Y, and M is the pair set which includes them as a pair. So yeah, this is the axiom of pairing, which lets you pair stuff, and this is important when you like have a lot of subsets. Essentially, you can there is also the axiom, if we go down, for power set, and the power set axiom actually depends on the axiom of pairing. Without the axiom of pairing, you can't have the power set. Okay, so the next axiom is the axiom of union, right? So if you have any set S, then there is a set A which contains every set that is a member of some member of S, right? So that sounds confusing, but all it's saying is that if you have a set S, then there is a set A which contains every set which is a member of some member of S. So essentially S has a lot of sets, some of them like their subsets, and then there is a set A which is which contains every set that is a member of the subset of S. So let's see this logically. So logically saying that you have a set X, then there exists a set U such that for all the sets Y, the right, so the set Y is contained within U, and that's equivalent to saying that there exists a set S such that Y is in S and S is in X, right? So Y is in the set S, and S itself is a subset of X, right? So this leads you to forming a chain of subsets, and what that means is that you're actually getting a set of set whose elements are subsets of some other set. So this set U is actually the union of all the X's, right? And So that's the chain you're creating. So I hope you've seen this kind of notation before, the cup and the inverted cup for intersection and everything. So the book actually goes through that, but we didn't necessarily go through that. So then you have the axiom schema of replacement. This is also kind of a tricky one. So this one says that if the domain of a definable function f is a set, and f of x is a set for any x in that domain, then the range of f, so the range is like the image of f, is a subclass of a set, which is subject to restriction. So this is kind of tricky because we haven't yet got to function, so we don't know what how to actually think about functions, right? But the thing is, you don't really have to have a function. You can actually try to think about it in terms of relations. If you know relations, so yeah, we have to let this go as of now, and we'll come back to this when we have gone through functions. But the idea of this, if you know what a function is that if you have a function which is definable on a specific domain, then the image of that function is going to be a subset, right, of the codomain, and when it's restricted, it's perfectly definable, right? So when you restrict, for example, if you have a function f going from a to b, f restricted to a is going to be is going to give you the image of a, right? And that's the schema of replacement. It's used a lot, but mostly you don't really use this act as an axiom because it kind of comes along when you deal with functions. Okay, so we have the axiom of infinity, which is kind of an important one. So yeah, so this is what it says. Let S of x abbreviate x union x, right? So S of x is a set which contains union of a set x with itself. So you're essentially making chains of the same sets. So there exists a set x, capital X, such that the empty set is a member of x, and whenever a set y is a member of x, so whenever you have another member of x, then S of y is also a member of x, right? So this is just a tricky way of saying that you have a set x, and empty set is included in that set. And so now we define this property. So this property says that whenever you have another member of x, S of y, remember what is S of y? S of y is just y union y, so the chain of the same elements with the union, then that is also included in the set. So this is what it says. There exists such an x such that when you have the null set in x, and for all y, if y is an x, then that implies this is not how it's supposed to be. This is supposed to be S of y actually. This is a typo. But yeah, S of y is also an x, or y union y. So a very interesting example is how you do this is if you have a set x, and then you take again the null set to be in it, then this null set is an x, but this singleton, right? So this set including the null set is also an x, right? So what you do is you repeat this process. You repeat this process until eternity. You have the null set, then the set including the null set, then the set including the set including the null set, and you do this repeatedly, and you have this chain, and you have a new set. and you can actually like denote each of the these sets such that like this null set, which like isn't included in any other set, it can be 0, then 1 is this singleton, then 2 is this uh, set within itself. So like this you can have the entire whole numbers actually. So yeah, that was the axiom of infinity. Sorry, I think someone just asked a question in the chat. Let me get to it. Would it be possible to introduce some of the problems to be solved before mentioning the axiom rules that are related to solving the problem? I'm not sure, but like, are you asking like some kind of problems that we should solve using the axioms? Oh, okay. That would be good. But the thing is, when you try to prove things, um, okay, so you like essentially examples, right? Okay, okay, so that's a good idea. Yeah, because these axioms are pretty abstract. Yeah. Um. Okay. Let's see. I think I have a set of notes which does that. Let me get to it, and I guess that's a good idea. We can do that. Mm, let's see. So this right. So I believe this the set of notes actually goes through each example. Right. Okay. So for example, this is the axiom of union, right? So here is an example. If you have A and B as sets, then the singletons containing just A and just B are sets by the pair set axiom. Yeah. And hence you can uh, have X which contains these singletons as elements, right? So that again is a set, um, again by the pair set axiom, apply again. So then the expression, this union of X um, is going to be a set again. So this is essentially, I mean, uh, the examples are pretty much straightforward, or they're either straightforward or they need like a lot of axioms to conclude them. But you kind of try to repeatedly apply the axiom. This one is an interesting one, right? So if you have this n number of sets, a1 till an, you can define recursively this kind of relation. So we have this set containing all the n sets with n plus 1 as well. So this set can be defined as the union of this set with this set, right? So this is how the union works. You take two sets and then you can like pair them to make uh, 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 a bigger set. Okay, so that was for the union axiom. But yeah, if you look through these, you can't have examples for the most part because using the examples needs furthermore axioms, right? For example, this theorem that I just told you, to practice kind of think about that there is only one empty set. Uh, this looks simple enough, but if you actually deductively go through each proposition and each following each axiom, it takes a long time. Formally, it's pretty long if you try to follow using the axiom. So that's why giving examples of axioms is kind of hard because they are abstract. But yeah. Mm-hmm. Yeah, for sure. I'll link this document up there, or maybe I'll just like you know uh, use some of these examples in my notes and then upload my notes. I'll do that. Thanks. Okay, so yeah, let's continue with our axioms. So we have the axiom of power set, which says that for any set A, you have a set which is called the power set, whose elements are all the subsets of A, right? So this is directly from the axiom of pairing. Um, if you have a set A, you have its subsets, and you can pair each of those subsets with each, you know, with each other, and then you can create um, bigger and bigger sets until you reach the biggest possible set, which is the power set, right? And if you have seen set theory before, for any set of n elements, the power set contains 2 to the n um, elements. So yeah, that was the axiom of power set, and it's almost always important because you're going to use power sets for everything. Um, then the last one is the most controversial of axioms, the axiom of choice. Some people like to include it, some people don't. It's still a controversy. I don't want to get into the controversy. Um, but the axiom of choice is this one. The other kind of incarnation of axiom of choice is Zorn's lemma. That's kind of complicated. We might meet it some, yeah, I think we'll meet it at some point. But as of now, we can just go to the axiom of choice, which is that um, you have a set and all of its members are non-empty, right? Then there exists a function f from x to the union of the members of x. So let's think about this. You have x and you have a function which takes you from x onto the onto another set where you have the union of the members of x, right? And they're not the same thing, right? Um, so this function is called the choice function. So what it lets you have is that for every member y in x, f of y is also going to be in y, right? And this sounds kind of like both trivial and paradoxical, but this is just like you have a set and you have another set which contains the union of its elements, right? So if you have, let's say, the set X contain the elements A, B, and C, then the other set which you're taking the function to is the union of set A with set B with set C. So it's the union of the elements. So what this function lets you have is that uh, if you're going from, let's say you pick one set in X, right? So let's say the set A containing the singleton A. So then f of A is going to be within A, because again f goes from here to the union of elements. So you're actually going inside the set again, and so this kind of like lets you like uh, give a choice in some manner to do this. We probably won't need much of it. We might, I'm not too sure, because we're like going to a lot of books, so some books don't like to include axiom of choice at all, but most books do though. But yeah. On chapter 3 of Turnstall's analysis 1 for the axioms and the Russell's paradox. Yeah, I was talking to Balto the other day, and he was saying how the analysis by Tao is actually very both like it starts from the very basic and like does a good job at it. Okay, so that was for the axioms. We covered it. The book doesn't cover it, and the presets are not going to be using these, but these are actually very important to know. Okay, so now we have this brief section on binary relations. The book also doesn't cover binary relations, I believe, but we're going to need that for defining what an equivalence relation is. So a binary relation on a set is a two-variable propositional function. So what this does is it takes two elements, an ordered pair of those elements, and then it gives some propositional value about it. So either it's going to be true or it's going to be false. The relation between the elements that it picked. So more precisely, if you have a binary relation R on the set E, then it has a bunch of properties, right? So if the binary relation satisfies this condition, then it's reflexive. So okay, so we're going to go through these conditions. Mostly you would not need more than the first, second, and the fourth one, because those are the ones that we need for equivalence relation. But it's good to know the other ones as well. So for reflexive property, every element in E, when you apply the relation to itself, it's true. The relation is true, right? So it gives you the true value. So R of x comma x, so this is read as relation of x with x, right? If you had y, it will be relation of x with y, and that's true. So that's when it's reflexive, right? So the symmetric, so the binary relation is symmetric if you take two elements of the set E, and then you apply the relation to those two elements, and then you reverse the order, and the relation stays the same. So this says that R of xy is equivalent to R of yx. Right? So the relation doesn't change when you change the order of the elements. So that's when it's symmetric. When it's anti-symmetric, it's exactly the opposite, right? You take the two elements. So if you have like R of xy is like and R of yx, if you take those two statements essentially, I mean, yeah, these are statements that like the relationship is true. Like if you have like both of them to be true, then that must imply that like these elements are equivalent, like they're the same. If that's like antisymmetric, right? Right. So that's antisymmetricity. So then you have transitivity. So it's transitive when you have like three elements, x, y, and z, and rxy with ryz implies that rxz holds, right? So if the relationship between x and y holds, and the relationship between y and z holds, then that implies by transitivity that the relationship between x and z holds, right? So yeah, that's transitivity. And a binary relation is total if you have again x and y, but for all x and y, um, either R of xy is true or R of yx is true. So both of them cannot be true at the same time, right? So it's kind of like the antisymmetric, that like if both of them are like true at the same time, then that implies x is equal to y. But here you don't really have anything about x, y being equal. You just can't have the relationship between two elements in both the directions at the same time if it's total. Right. So that is what a binary relation is. It gives you a relation between two elements of a set, roughly speaking. So one of the special cases of what a binary relation is this thing called the equivalence relation. So an equivalence relation is a binary relation which satisfies these three properties. It is reflexive, it is symmetric, and it is transitive. Right? So if you have these three properties, your binary relation is an equivalence relation. And most often we're going to denote it with the tilde. So that's the equivalence relation. Now, if R is an equivalence relation on the set E, then what you get is you get, okay. So this is the from the axiom of, what was that even? I forgot. It was the axiom of the property one, right? Specification, the axiom schema of specification. Yeah, restricted comprehension. So you have the equivalence relation, and now what the equivalence relation does is that it picks elements from the set E that satisfy the equivalence relation, so they can be related using the equivalence relation, and then you create a subset of the set E, which includes all the sets that satisfy the equivalence relation, and that is called a partition. Um, we don't really talk about it here, yeah, but we're going to go back to Luffy where he talks more about it. So if R is an equivalence relation on the set, the class of equivalence of an element X is the subset denoted by X of elements Y in E, such that Y and X have this equivalence relation, so they satisfy the equivalence relation. So right, so for every element in the set, you have an equivalence class. So equivalence class is like the all the elements. Uh, so like for example, if you have A, the equivalence class of A is like all the elements in the set with which you can pair up, with which you can like have the equivalence relation, right? So that is denoted by this symbol X within close brackets, and yeah. So that's the equivalence class, and this is very useful in pretty much every area, but one of the areas where it is um, something like that I've seen a lot recently is in algebraic topology. If you have seen anything in algebraic topology, we're always using equivalence classes, right? But yeah, that's another story. Apart from this, we also get a quotient set. So the quotient set is actually the partition I was talking about, right? So the quotient set is the set E and slash this tilde. So this notation, kind of, you can think about it kind of like division. If you've done modular arithmetic before, you know about modulus, mod, but if you haven't, then this is like you have the set E, and then on the set E you impose this specific relation on the entire set, and when you do it, you get a subset of it, which is the partition, and then that is actually the quotient set. So this is E slash tilde. We're going to use this extensively, as I said, because this is kind of like one of the fundamental things for with which we can do a lot of things. So that was about equivalence relations. So now let's get back to the book. Okay, so yeah, in the book contains a few examples. We should go through these examples to get the idea of the equivalence relation clear, right? So yeah, and the idea about partitions in general. Okay, so yeah, so here we have a more descriptive definition of partition. So partition of S is a family of disjoint, non-empty subsets of S whose union is S, right? So a partition, as I said, is like the set you get after applying the equivalence relation. So it kind of like divides the set into partitions uh, according to the rule that the equivalence relation follows. So let's see, you have the curly P here, which is a partition. So it contains this set of 147, 258, 36, and 9. So it is a set containing 4 sets, right? So it's a partition. So it's a partition of this set which contains 9 elements, the 9 numbers. So how you get from this set to this is by applying an equivalence relation which picks these numbers, right? These numbers and partitions them into each set. Right? So here's how you actually get it. So for every element A, yeah, we just talked about it, the equivalence class of A with respect to this relation is the subset such that is the subset containing all the B's which are definable under the equivalence relation with A. So all the partners of A in a sense for this relation. So then the equivalence classes form a partition of P total of S. So what you have is that these equivalence classes are defined for each element, right? So for each element you can get these kind of sets, right? So you get these kind of sets. For example, let's see here. On this set we define some kind of equivalence relation tilde such that we identify. So this is also set as identifier. Sorry. So this can be read as B tilde A is read as B identified with A. So so we can identify 1 with 1, then 1 with 4, and then 1 with 7, right? So that's how we define the tilde to be. So again, what is the equivalence class of 1 in here? So the equivalence class of 1 is precisely this, because that's how we define the relation to be. It identifies with these 3 elements, right? Then you do the same for each of the elements. Then you're going to get these sets, and then you have the partition of the whole set. Right? So that's how the equivalence relation works. Yeah. So we have this example using the integers. So if you have the set of integers and the relation that you have is that you identify A with B if and only if. So this symbol is just of if and only if. So A is identified with B if and only if the difference between them is even. So A minus B is even. Right? So you can have you can think about like what it would look like, right? So Z is the set of integers. You can have -1, -2, 1, 2, whatever. So let's see. 3 can be identified with 1, right? Because 3 minus 1 is 2, which is even. Then let's see. 4 can be identified with 2, because 4 minus 2 is even. And in this manner, you can think about the number of relations, identifications you can create with each element. Right? But the thing is, if you go with this, you're going to actually have just two equivalence classes, that is of 0 and of 1. So this is how it is. So for let's see the equivalence class of 0. So the equivalence class of 0 is all the elements in the integers, all the integers, which when subtracted with 0 gives you even. So that would be the set of all even numbers, right? If you're considering the positives, so that will be 2, 4, 6, 8 dot dot dot. So that will be 1. And then you would also have let's see, for then the equivalence relation for 1 is going to be all the odd numbers, right? The all the odd numbers when you take the difference with 1, you're going to get even difference. So that's how the quotient space of the integers with this relation is just this, right? And this is how is helpful, right? Because you don't really have to worry about like each element of the quotient space, or each element satisfying the relation. If you can um, find a relation and apply it to the whole set, um, it should just work, and then you can get the quotient space, which lets you do a lot of things with it, which we're going to see later. But the direct consequence of this is modular arithmetic, which we're going to see when we do groups next week. Yeah, Artem does it in the second chapter, groups. Okay. Yeah, so this is a very helpful explanation that one way to think about this operation of the equivalence relation is that once you have the quotient space, these elements A and B are equal, are considered to be the same elements, right? So they become equal under this equivalence relation, and that's why it's important you can make things equal using this relation. So that was about set theory, about equivalence classes, and we completed a section of set theory, and we're going to give another hour to functions. Any questions on set theory as of now?
I had a question.
Sure.
So I don't really understand the Zernello Frankel. Sorry if I'm saying that wrong. The original axiom, the first one. Isn't that part of the well-ordering theorem?
Yeah, it is, except you can't have the well-ordering theorem without the axiom.
Okay. So,
Yeah.
so say I wanted to create a system capable of rendering infinite sets. If we chose a starting point, like an origin, then there would exist an element within an infinite set that requires infinite space to render. So we really wouldn't be able to choose an origin. So I don't really understand how you could represent infinite anything in this system.
Okay, so if I understand you correctly, so you're saying if you have an infinite set and you start from the origin, you're saying like if the infinite subsets are not going to include the origin?
Like, I can use an example.
Okay.
So say we define an origin, right? And we just wanted to represent a single particle. Let's just assume that that particle is so far away that it would be impossible to ever represent that particle because we don't have infinite space to even represent that vector. So then how could you represent infinite anything if you choose an origin? Wouldn't it mean that you would have to apply the same rules to every location in space? in that particle system?
Well, that's well. Then you're saying the thing is the axioms of set theory have nothing to do actually with anything existing in the real world. Um, that's precisely because the way it was formulated was that once you can like follow the logic, you don't really care if you can. The thing is, the logic, the axioms allow you to have infinite sets, right? Um, but whether you can actually have infinite sets, like a set which actually in somehow like represents infinity, that's a question the axioms don't have to answer, right? And this is again, this is like typical of the things that set theory, foundations, logic, even analytic philosophy deals with. It's kind of like, again, the example that you gave is about the physical world, right? That we can't represent a point that is like so far away, and we don't have the we can't formulate it using vectors, right? The position vector, we can't um, precisely write it down. But in theory, the set theory axioms are going to say to you that um, you can actually formulate the distance using the subsets. Like the thing is, you can like have a vector until some point, right? So if you can have that, you can like repeat the process and use the chain to get there. But if you're actually going to get there, is not something that can be said using the
I guess
axiom.
I'm saying if that position is actually truly infinitely far away.
You can say
there's no frame of reference that you could pick to where it stops.
The thing is, how do you know whether it actually stops? It's like
well, that's what I'm saying. You wouldn't even be able to tell if it
yeah,
would stop because there's no frame of reference that you can choose.
yeah. The thing is, if it stopped, it would not be finite. Sorry, it would not be infinite, right?
Exactly.
Yeah. So that's tautological. It's kind of circular logic, right? The definition of infinity depends on itself. That's precisely because we can't yet formulate anything precisely as infinite. Because again, what does it mean to formulate um, infinity if formulation itself dependent upon finite things? So yeah.
I just don't see how you could choose a single origin to hold precedence over any other origin in an infinite system.
Because I mean the thing is like okay, if you have the origin and you have the infinite system, it like the promise isn't that like you'll be able to go as far as you can and still like have a connection with the origin, or like be able to get from the origin to there. um, the promise is that the infinite point itself is possible, like exists because of the subsets, as I said. But yeah, I'm not sure if what you're saying has something to do with the axioms themselves, but more like how they're applied.
I think it's just more I have like an issue with the well-ordering theorem in describing infinite systems.
Okay, so we didn't see the well-ordering theorem, right? Let's see that.
Well, I figured the well-ordering theorem is part of the axiom of choice, right? Or you can derive the axiom of choice from the well-ordering theorem.
Indeed.
I'm not entirely certain.
Um. Okay, so we shall continue with the functions, um, I guess, and we'll see. Yeah, but Balto is right. Yeah, physically you don't have infinity per se. Um, hmm, okay, so we have actually a bunch of things to go through for functions, and they're all important. Um, the injectivity, surjectivity, there are two different ways they approach it, um, and some of the ways they prove it. So yeah, let's see how much we can go through. I'm not going to go through like each of the proofs, because that'll be too long. But we'll try and discuss. Okay, so what is a function? Okay, so the function is well, they don't actually define it here, but a function is such that you have a relation between two sets, such that for any given element of a set, you have precisely an unique element, which is its image. So this is actually the graph of a function. So the graph of function, they denote it with the gamma sub f. So it's the graph of f. It's a subset of all the ordered pairs AB from A cross B, such that B is the image of A under F. Right? So this is going to be yeah, all the pairs AB, such that the latter is the image of the former. Um, and this graph is going to be a subset of the Cartesian product of the two sets. Okay, so yeah, not all the subsets of gamma like correspond to functions. Not necessarily, but for a function, what we need is this condition actually, that for every element A in the set A, there exists an unique B such that f of A is B. Right? Uh, that must be the case for it to be a function. And then you have the notation f from A to B, the typical way. Yeah. So this is one of the special functions. So this is the identity function. So the identity function takes you from an element in the set to the same element in the same set. So it's essentially just going from the same set, from the same element to the same element in the same set. Um, okay. Right? And then you define what is the image of A. I already told us, but if you have like S as a subset of A, then f of S is going to be a subset of we denote by f of S the subset of B defined by yeah. So f goes from A to B, right? So f of S is a subset of B, which is like the set of all the images of F. Mm-hmm. Okay, so Yeah, this is kind of important because the notation is can be confusing sometimes. When you have indices and functions. So if you have a1 till an are integers, um, what we're doing when we write this as a sequence or anything, what we're doing is we're taking a function a uh, of the natural numbers from 1 to n, and we're mapping them onto the integers. So, right, so we associate each integer with uh, one of these numbers, right? So uh, some integer with 1, 2, and you go on, and then you have the sequence. So this is what you should remember, right? When you have a sequence, it's actually a function from the natural numbers. Right. Yeah. So this is also important, right? So it's common to think that the indexed set, right? So this indexed um, this index set is like the set of AIs, where I is like belongs to this index I, capital I, right? So this index set simply is a set whose elements happen to be denoted by AI for I ranging over some set of indices I. So this is like how normally we want to think about it, but that's not really what it is. It's actually, you have to think about it as a function, right? So more properly, it's a function from this index that we have I onto A, uh, which has elements these AIs, right? And that's how you get this indexed set. And we're going to use the indices a lot, so yeah, that's important. And then you have the typical way you define the composition of functions. So if you have functions f and b going from a to b, then b to c, then you can have g circ f, which goes from a to c. So yeah, you probably have seen this before. But yeah, so the composition is one of the most basic and almost always used things in functions and maps. And these diagrams are what we're going to meet on Thursday. We're going to use a lot of them for category theory, but this is how you present uh, the uh, the mappings of the functions. Yeah. So like these diagrams are actually what you call as like are commutative, or the commute. So what it means for it to commute is that if you take like the composition of these two functions, you're going to get this one, right? So f circ g, g circ f is going to give you this function. And then if you like do it in any other way, you're going to get the other function if you take the composition of the other two. Um, so that's what it means to commute. You can like travel around um, following each function as it is defined. And yeah, one of the properties of composition operation is that it is associative. So h circ g circ f in parentheses is equal to h circ g parentheses then circ f. Okay, so you can move around the parentheses, and but the composition still stays intact. And this is pretty much straightforward from what we've defined as the composition. So yeah, that's about the basic stuff. We're going to see the injectivity and subjectivity, and then we have some interesting results. not interesting. I mean, you've seen this before, but yeah. And yeah, let's see. So we have some classifications of functions, right? So a function is injective if it's like 1-to-1. So for example, no two elements can be mapped to the same thing, right? So the image of a prime can never be equal to any image of any other element under F. So F of A prime is always um, unequal to F of A prime. So yeah, it sends different elements to different elements. So that's injective. Then what's surjective is that it sends one element at least to another element in the codomain, but it can send to more than one element, right? So um, for all B in B, there exists A such that B is equal to F of A. Right? So F, quote unquote, covers the whole of B. But yeah, more like the image of the function is the codomain itself, right? So each of the element in B is always mapped. Sorry, mapped by something in A, right? So for every element in B, you can find another something in A such that is mapped to B, right? So yeah, B is always covered, or more like B is like no element of B is missed. Okay, so and when you have like both of these properties, you get the bijectivity, right? So the bijectivity is also the isomorphism between sets. So that's bijectivity is like when two sets are isomorphic, you can say. So bijectivity is like injectivity and surjectivity. So it's like you have a complete one-to-one correspondence from each element to another element, right? So it's the like ideal kind of um, correspondence you want between two sets, right? So every element is mapped to something, and they're mapped to precisely one thing, and yeah. And when you can have this bijectivity between two sets, you can write them like this, and that makes them isomorphic as sets. And we're going to have isomorphism and different things as we go along the course. The next one that we're going to meet is going to be the group isomorphism. But its isomorphisms are always bijective, no matter what objects they're dealing with. And yeah, quite obviously, the identity function is the bijection because you're mapping the same thing to same thing. So it's always something injective and surjective. Okay, so if A is isomorphic to B, so that means you have a bijection from A to B, then the sets A and B can be quote unquote identified through F, right? So F allows you to like identify each element of A with some element of B, and you can do that for every element, each of these elements, and then what you have is like a unique way of identifying every element with this function, right? So these sets are now identified, or they identical under this specific um, function, right? So yeah, in the sense that we can match precisely the elements of A of A with the corresponding elements F of A of B. Yeah. Yeah, so this is like a corollary that if A is a finite set and A is isomorphic to some set B, then B also has to be finite because you have an isomorphism. So like um, like there can be finite many finitely many correspondences from the elements of A in the elements of B, and so that means B has to have finite many elements, and also that the cardinality of A is equal to cardinality of B, because each of the elements need to be mapped to a specific thing. So yeah. Okay, yeah, okay. You know what? Once we go through this, we might have some time to discuss about the well-ordering theorem. It's an interesting thing, yeah. So I don't want to discard it, but just that we should just cover the important thing that we need to in the lecture. Yeah. Okay, so that was about the bijectivity and the um, the classification of functions, but we have like a second viewpoint here as well. It's kind of the same thing, but it's in terms of the graph, as we saw before. Yeah, and it's kind of interesting. So let's see. So if ff is actually a bijection, then we can flip its graph, right? So flip its graph in the sense that you can like make the codomain its domain, and you can like define a function from there. So you have g um, defined from b to a, that is, and we can let a to be g of b when b is equal to f of a. Yeah, so this is like you try to like define a function in the opposite direction, and like so that when you compose it with the original function, you get the identity on each of the sets. So this is very interesting. So let's see. You have f going from a to b. You have g going from b to a, right? So if you have a g composition f, right? So g composition f means g comes first. You do sorry, f comes first. You do f first. You go from a to b, and then you use g to go from b to a, right? So when you have g composition f, but you end up is at a. So essentially, eventually, as f is a bijection, um, and so is g, um, you eventually end up with an identity map, right? So the composition of these two maps gives you the identity function that maps the same element in A to the same element in A, right? And if you change the order of this composition, you end up with something similar, right? Then here you first do G, then you do F. So this is F composition G. And what this leads to is that you have an identity map over B, right? So yeah. Hello, Killer Whale. Thanks for joining. Would you mind if you can mute your mic, please? Yeah, thanks. Okay, so yeah, so this leads to two interesting things. Is that you can get the identity of these two sets using the composition in two different ways, right? So the first identity, so the identity of A, tells that G is a left inverse of F. So the left inverse, what it means is that when you can write G on the left side of F and then take the composition, you get the identity, right? And the second tells us that G is a right inverse of F. So like if you even use the composition on the right side, you get the identity too. And what this means is that like G is the inverse of F. If it's also right inverse and it's also left inverse, then it's actually the inverse of F, written as F to the -1. And thus we can say that bijections always have inverses. This is not really like a strict proof, but you can do something with it, and then you can prove it that every time you have a bijection, you're always going to get the identity in these two ways, and then they are going to have inverses. Okay, so what about the converse? If a function has an inverse, then does that mean it's a bijection? Not really, and this is how it is. So assume that A is not the null set, okay, and f goes from A to B is a function. So then you have two propositions, right? The first one is that f has a left inverse if and only if it is injective, right? If f is injective, then it has a left inverse, and if it has a left inverse, then it is injective. If and only if is like a two-sided equivalence. The same for right inverse, except for surjectivity. So if you have a surjectivity, then you have the right inverse. So now he goes on to prove these two things. Essentially, he does the first one, and I believe he does it quite rigorously. But yeah, let's go through it, pretty quickly. So again, like every if and only if statement, you have to prove both directions. So the first direction, the implication, in the from having a left inverse to being injective. So if f has a left inverse, then so then there exists a g from B to A such that G circ F gives you the identity on A, right? That's what we just defined here. Now assume that like A prime and A double prime are two like distinct elements in A, right? So what you do is you apply this G circ F to these two elements, and you're going to see that G of F of A prime gives you the identity of A prime, which is A prime itself, and the same for A double prime. So the point is that like when you apply the function on two different elements, you always get two different images, right? And that's the definition of injectivity, that different elements get mapped to different elements in the image, right? So that makes it that's like halfway through the proof. And now the other direction is when f is in we assume that f is injective, then we have to show that it has a left inverse. Now this is kind of a bit lengthy, but let's see. So yeah, all right, so we have to first construct a function, right? And then show that when we compose it with f on the right side, on the left side, we get the identity. Okay. So so again, by definition, a function must have a unique g of b, the image for each element in B, right? For this, choose any fixed element as yep. Okay. Then set g of b to be a if b is equal to f of a, right? So if g of b is like you define it as a function, as a piecewise function, it gives you a when b is the image of f of a for some element of the set a, or it gives you s if b is not at all in the image of f, right? Now what we are going to show is that like it is indeed the first case. Let's see. So in words, if B is the image of an element of A, send it back to A. Yeah. Otherwise, send it to your fixed element S. Yeah. It gives you A if you have some image. If you don't, then you just go back to the fixed element that you picked. Right. Okay, so this is actually a defined function, right? And f is injective, right? F is injective, so we can like actually have like different elements separately mapped to different things. So this guarantees that every B that is the image of some A by F is the image of a unique A, right? So like you have unique elements mapped to unique elements. Okay. Mm-hmm. So what this says is that every B is sent to a unique well-defined element of A as is required of functions because of injectivity of F and because G is actually a function. So what happens is that G happens to be the left inverse because the second condition that we had for giving us S, that actually never happens. It always gives us A, and that is like the element itself, so it gives you the identity. Yeah. So that means G circ F is the identity, and thus it's the left inverse. And the other one is an exercise, but it's essentially the same thing, just done for subjectivity. Okay, so we have a corollary of this, which is that a function is a bijection if and only if it has a two-sided inverse. Right? So you have a two-sided inverse in the sense that like if f and G, f if G is an inverse of F, then F is also an inverse of G. So that's two-sided inverses, and we're going to see more of that. But we have this proposition which is like pretty long. um, I don't think we'll be able to cover that, but yeah. Hmm. Okay, so let's see about this corollary. So if a function is injective but not subjective, then it will not have a right inverse, right? So if it's just injective, then it has a left inverse, but this says nothing about the right inverse. It will never have a right inverse actually. Um, mm-hmm. Similarly, a surjective function will have more than one right inverses, but it's not going to have left inverse, right? And these right inverses are actually called sections. Um, I'm not sure if we are ever going to meet that again, but sections, like I've heard of them in differential geometry. Um, Smooth sections are vector fields in tangent bundles, but yeah. So sections are essentially surjective functions that have sorry, sections are the right inverses of surjective functions. Yeah. Okay. Mm-hmm. right? So yeah, so this proposition that we just saw, which said about like left inverses with injectivity and right inverses with subjectivity, what that allows is that it allows us to like even if we don't know what's happening at like in the elementary level, like knowing what element is mapped to which element, we can know about the properties of those elements, right? So yeah, that's what he says. Even if we did not know what elements means, still we could make sense of the notions of injectivity, right? Those are that's the property that's the property of the sets, right? By exclusively referring to the properties of the functions. So yeah, and this is going to be something that we'll see in categories. Yeah, so this here is can be a bit confusing. So the inverse of a bijection is f to the minus 1, right? But we have something else which looks similar, but it's not the same thing. So if f is a function, any function doesn't have to be bijective, and you have a subset of b that is t, then f to the minus 1 of t, this is read as the pre-image of t under f, right? And that denotes all the elements from A, all the elements, yeah, of A that are mapped to T. That's the pre-image. And apart from being called pre-image, like if you're like considering like pre-images of like specific points, then those are called actually fibers. This again comes up in algebraic topology and differential geometry, and we're going to use it at some point when we do something related to that. But yeah, so these are like this has nothing to do with bijectivity or inverses, right? So these are sets. F to the minus 1 of t is a set which contains the elements that are mapped to t. The same way, if T is just singleton containing a single element, then the preimage is going to be the fiber of F over Q. Right. So yeah, if you think about this, if like for F to be a bijection, um, like the fibers of all the elements of B. So if you look at like the preimages of all the elements of B, they are always going to have something in them, right? So something in them, that means like something of B is mapped to something of A, which is by definition surjectivity. And the as is bijective, it means that the fibers are actually singletons. So the fiber of F over any element of B is actually a singleton, a single element. So that's injectivity, that every single element is mapped to some other single element. So the one-to-one connection. Okay. And then we have some other definitions, and we'll be done for today. Let me get some water. If you have any questions, you can ask. But yeah, I'll be right back. So there's a discussion about the well-ordering sets. Yeah, it's interesting. We'll see if we can get to it after we're done with the lecture. Okay, so we have two more kind of functions, monomorphisms and epimorphisms. Right? So it's another way to express deal with injectivity and surjectivity. Um, but yeah, it sounds complicated, but it isn't. So a function f um, from A to B is a monomorphism, or as is often said, monic, if the following holds. Right? So what it holds is that for all sets Z and all functions alpha prime and alpha double prime, which go from Z to A, right? So you have some sets Z and you have some functions alpha prime and alpha double prime that go from Z to A. If the following holds, which is that f circ alpha prime is equal to f circ alpha double prime, means that alpha prime and alpha double prime are equal. So if that's the case, then it's a monomorphism. So yeah, so how to think about this is that you're going from A to B using f, right? Now you have some other set Z, let's imagine it's on the left. Then you have two ways of getting from Z to A using alpha prime or alpha double prime. The condition is that let's say you take the composition of the two ways, the two functions, f circ alpha prime. So f circ alpha prime is going to take you from Z to B, right? Um, and the same f circ alpha double prime is going to do the same from Z to B. The condition is that if both of these functions actually happen to be identical or the same, right? The compositions happen to be the same, then that implies these maps that we took to get from Z to A are the same again, right? So this is like pretty straightforward, but let's just do a few things with it, right? So the proposition is that if f is injective, f is injective if and only if it is a monomorphism, right? So and we have the proof, um, which is pretty long considering we have other things to go through. Does like do you guys like want me to like go through the proof like bit by bit? I can. We can like try to go through it, skim a bit. But if you can like say that it looks good to you, then you can just skip.
Can you repeat that, please?
Yeah, so I just asked like if we should if anyone actually wants me to go through and explain this proof about injectivity and monomorphism, or does it look good to you so that we can skip?
It looks fine to me, but I don't know what the other.
Yeah, if anyone actually wants me to go through it, I will go through it. But if everyone's fine, then that's fine. Okay. Yeah, so the idea is again, you have to like prove the two-sided thing, um, and essentially you have to use the fact that it's injective means it has a left inverse, right? Like for the forward direction, you can use that to say that like those two things, alpha prime and alpha double prime, are equal. And then for the other direction, that's kind of complicated, but you can use that as it's a monomorphism, um, thus alpha prime and alpha double prime are equal. From there you can prove injectivity. Yeah, it will take a while, but yeah, it can be a good exercise to go through. So yeah, we have some basic examples, and yeah, and another proof which will look short. Okay. So yeah, so there are some basic examples of injective and surjective functions. So this one is about the projections. If you have done algebra before or some kind of algebraic things, you know this already. So if you have two sets A and B, and then you take the Cartesian product A cross B, then there are natural projections, right? Which what they do is that they let you go from the Cartesian product and take each of these components out. Right? So you can take each of these components out. So pi sub A, what it lets you do is you go from A cross B and you get to A, and that that's how you can like pull out, roughly speaking, from the Cartesian product one of the factors. Right, so how it's defined, how you define it is that pi sub A, you apply it to an ordered pair. Remember, because A cross B, right, the Cartesian product is the elements of ordered pairs. And so you take one of the ordered pairs A, B, and when you apply this function, you just get A. You pull A out of it. And when you do it for every other pair, you just pull out the A's, you get the set A. Right? Same for B. So these maps are surjective, as you can clearly see, because every element of A is pulled out for some ordered pair of A cross B. Right? So you always have something from the image in the code in the domain. Okay, so so naturally from projections you can actually have injections um, to the, but like instead of having the Cartesian product, we have the disjoint union this time, right? So what you have is like you have two different sets A and B, then you can inject A into the disjoint union of A union B. So what you do is you take the elements A of A, cap set A, to the corresponding element in the isomorphic copy A prime of A in A disjoint union B. Yeah, right. So again, in the disjoint union, you have a set which is isomorphic to A. It's not exactly A, but it's isomorphic to A. Essentially, that every element of it is the same. It can be identified using a bijection, and you can send these elements to there, and you do the same for B, and that gives you a way of injection, right? And yeah, so yeah, that lets us do a lot of things actually, um, um, because if you think about it in topological terms, this is basically what you call the immersion, um, inclusion, and stuff like that. But yeah, so okay, so let's see what we have. We have another example. So if tilde is an equivalence relation on a set, then yeah, so you can have a projection from the original set to its quotient set, right? So what it does is it takes elements of A and it maps it onto the equivalence classes of each of those elements, and that gives you a surjective map, and does function, surjective function. Okay, so I think this is the last section. Yep. So we have something related to the canonical decomposition. This is also interesting. So let's see. How long is this lecture? It was supposed to be around 1.5 to 2 hours. Yeah. Okay, so let's see. So what we observe is that every function f from a to b actually determines and lets us have an equivalence relation on A for all distinct elements of the set A. So how you do this is that if you have a function A prime tilde A double prime is like, sorry, A tilde is identified, sorry, A prime is identified with A double prime if and only if f of A prime is equal to f of A double prime. So essentially, if your image of two distinct elements is the same, then those two elements can be identified using some equivalence relation, right? So this function allows you to like identify the images of elements, and you can have an equivalence relation um, with that. So what we can do is we can actually have some interesting um, things using this, right? So f is any function, right? And you define the equivalence relation as we defined here. Then we can decompose f into in this manner. So what you do is you have f goes from a to b, yeah. But what you do is you first have a to a slash tilde, that is the quotient set of a, and then you have this f tilde, which goes from a slash tilde to the image of a, and then you have an injection inclusion into b. So we'll see that, but this is just the diagram. So yeah, so in detail, the first function is the canonical projection that we just saw before. It maps every element of A to its equivalence class, right? And the third function is the inclusion, right? So what it does is it includes the image of f, that is f of A, within B, right? And how it does that? Well, inclusion is just a way of like it's a subjective map that takes a subset and maps it onto a parent set. And you have these two sets, and between them you have this f tilde, which is actually a bijection. And how this f tilde is defined is that it connects the paths. It takes these equivalence classes and it gives you the images that you need, f of a's, right? Yeah. So this is how you can like decompose f into its into like kind of like sub functions, like essentially composition of these functions. So we have to show that like this diagram commutes and like f can actually be decomposed. So that's the theorem. Okay, so what we have to verify is that is like if we can define actually this f tilde as a bijection, then this path is connected, and we need the commutativity of the diagram as we want it to have, right? So yeah, so that's the key part of this proof, and we'll actually go through this because it looks important. Any questions? Okay, yeah, good to see that you guys are having an actual serious discussion about the axiom of choice. Okay, I have something to say about this, but we'll see. Okay, so let's see how we can do this. So the first item is an instant of a class of verifications of the utmost importance. Mm, right. So if you think about this f tilde takes you from the equivalence classes of the elements. Now, equivalence classes of each element is like a set of it's a very big set containing the other elements which are preserved under the equivalence relation. But what this f tilde does is that it chooses each of these elements, and then gives you the images f of a that you need. So what we have to verify is that if you have two distinct elements, a prime and a double prime, and if the equivalence classes of these two elements are equal, then that implies the images of both of them are equal as well, right? So so now let's see. So if you have the equivalence classes of two elements are equal, so what this means is that you can have an equivalence relation between these two distinct elements, right? So now they're no longer distinct. So a tilde, so a prime, is equivalent to um, um, a double prime, and so like by definition of the equivalence relation, um, what this means is that f of a prime is equal to f of a double prime. Right? It's because a prime and a double prime are equal under this equivalence relation. So like their images are also going to be the same, right? So f tilde is actually well defined, right? Now for the second item, or the second step, you have to show that this is actually a bijection, right? So we have to show that it is injective and surjective, right? So for injectivity, what you do is you have you apply f tilde on equivalence classes of two distinct elements, right? And you say that if the images of those under f tilde are equal, then the images under f of those elements are equal. Okay, so right, because we just showed that if by definition of f tilde, if you have two distinct elements, a prime and a double prime, their images are going to be the same. So a prime is equivalent to a double prime by definition of tilde again. Right? So again, yeah. So this is essentially just walking backwards, right? If we apply f tilde on the equivalence classes, we know that the elements themselves, a prime and a double prime, are equivalent under the equivalence relation. Um, so so what we showed is that the equivalence classes are equal. What this means is that it is injective, right? And this one is, again, you just follow the definition. So if you take B as like any image of f, then there is an element A such that f of A is B, right? And that's because it's an image. So if you have like some equivalence class of A and you apply f tilde on it, you get f of A, but f of A is just B as we assumed. Um, so this is from the definition of f tilde. But again, as we just picked any random B in the image, it shows that like we can do this for any other random element in the image, and thus it's subjective. Right? So this is actually a very important thing, the decomposition of any function using the equivalence relations. And yeah. Okay, so yeah, we're pretty much, yeah, we're done. And we have exercises. I would recommend you doing most of the exercises if you can. The ones that are like have some symbol triangle in it, they're kind of um, they look good. You can't like, I don't think the author says anything about it, but this is just what I've seen. But yeah, do the problems. The problem sets are pretty much going to be from here, so they can be a file. So yeah. Any questions or anything you want to say about before we leave?
I wanted to say thank you. This has been very useful.
Ah, that's glad to know. Yeah. If you have any kind of suggestions, do you like feel free to suggest any kind of like suggestion material or anything. I mean, the material can be changed because the schedule has been prepared like that, but yeah. Okay then. So yeah, let me take a look at the schedule again. The PSET discussion will be on 14th July. The PSET will be released on 8th July. That is Thursday. And you'll have around 6 days to solve it. Yeah. Yeah, and about the axiom of choice as you guys were discussing. Um, yeah, as Nick pointed out, the Aristotle's way of thinking was that, yeah, if you have an origin, then you are in a finite system. But I'm not sure if that's what the axioms are intending to say. Okay, so yeah, practice some set theory. Or if like I think I have this book, which was this Transition to Advanced Mathematics. Yeah, so this is a book on proof writing actually. It is pretty good. It has like proofs and like of different kinds. So you might like I mean we're not doing a course in proof writing, so but like you can like pick up certain things from certain chapters that would be helpful. For example, they have a chapter on group theory, proofs in group theory, that can be helpful. And even I think the chapter on logic would be helpful for someone who wants to know like about like how to make you know deductive statements in mathematical logic. So yeah. Hmm. Okay then. So we'll meet on Thursday for the second lecture. We're going to cover the sections 3, 4, and 5 of Luffy. You're recommended to just skim through it, and we'll go through it together. And yeah, we'll meet categories. Those are interesting things. So yeah. Till then, take care and see you on Thursday. Thanks for joining.